You hear me? Hello?
Yes, sir.
Actually, I don't know. I had scheduled, but I couldn't find it. So I just meet now. I'm doing it. I think ask the students to join. Okay. I don't know what I couldn't find the schedule and that. Okay, fine. Let me start that. Okay, let me see that. अभी क्या हो गया? उल्टा पलटा हो रहा है. Well, let me start. Page कौन सा है? 23. So remember that I started talking about. I started yesterday a Cauchy sequence. So let me go there. Be careful, it is different in convergence sequence. Cauchy sequence is informally. It means members are getting close to each other, but they may not gather around a point. Like here is an example. If you see that here, with the usual distance metric you take, then you look this sequence xn equal to 1 by n. This sequence, they are getting close to each other. It converges to 0, but 0 is not here. So that 1 by n is a Cauchy sequence by definition. Is Cauchy in 0 infinity, but not convergent. Okay. That I told you that it is a, may think of that this is not taking enough big metric space. Well, intuitively that is right, but the problem is in an arbitrary metric space you do not know whether how big it is, how small it is, whether it is contained in a bigger set or not. Okay, so that is the problem with the Cauchy sequence. Okay, now the look here. So I have given page 79. You should have this example I talked about. Now suppose here if I give another metric on x, this thing, this metric I give. Look, this makes sense because neither x nor y is 0. It's the metric. I have asked a question that d prime, suppose, right? Is x d prime complete? Think about it. Okay. Here you can see that if you take 1 by n, it will coming this. That is not a, first of all, 1 by n is not a Cauchy sequence here. Because 1 by n, if you take it the reciprocal, n minus n, that is not going to 0. So 1 by n here with this metric is not a Cauchy sequence. Okay, so it won't help. So think about, if you think complete, you'll have to show complete means if every Cauchy sequence converges. Okay, right? Now I have given the discrete metric space that I discussed, and in fact this is a special kind of discrete metric space. Look here, you are having n minus m, distance between n and m, which is greater than 1. Here also you will see that for this, you take r less than equal to 1. This will be actually also n. In the definition of convergence of sequence, actually you needed to deal with the both. So here you can also see that it is behaving like discrete metric space. So here, what kind of sequence will converge? Only the eventually constant sequence will converge. So that this is also complete. Okay. because it is basically same as example 2. Okay, now the thing is that I want to say this is a big theorem. I want to prove this, that this result, that with this is a complete metric space. That is, every Cauchy sequence in R, this metric, it depends on the metric, converges in R. Now look, in order to do this, you can see the proof, but so I'm not going to repeat the proof. You can see proof is very simple if you use Bolzano-Weierstrass, but the proof depends on this result. Actually, look, this is the result. Look, I am writing. This you can take an exercise. Let XG be a metric space. And Xn be a Cauchy sequence in X. Basically an XT. Suppose Xn has a convergent subsequence. Okay, convergent subsequence. Then what I'm saying, the sequence Xn itself converges. Look, its proof is what I have given the proof here. This theorem for the R is complete with the usual distance metric. Same proof will work here. This is the general thing. If you happen that Cauchy sequence has a convergent subsequence, that Cauchy sequence will have to converge. The idea is very simple. Cauchy sequence, the members I told you last time, the members are getting close to each other. But if you have a subsequence, then these are gathering around X. But members of the Cauchy sequence, after all, they are getting close to this, so that they will converge to X. This is the simple idea. So you need to apply triangle inequality. In fact, look at the proof at the end of the proof of this theorem. When I said Xn minus X, I have taken, look, I have taken this. This is the subsequence. Then you are doing this triangle inequality. Look, here you replace D triangle inequality. That will give you this result. Proof. So this is the proof is here. Okay, fine. Now the thing is that once you know this result, then it is immediate. Then with this result, you add Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem, remember that. It says every bounded sequence in R means with the usual distance. When you don't mention anything, the metric on R, it is usual distance metric. R has a convergent subsequence. Say again, what you were saying, something?
Limit point.
Huh?
Every boundary sequence has a limit point. Yes, sir, you will say.
Every bounded sequence in R has a convergent subsequence. This I proved. This is a corollary to limit slope. Look, every bounded sequence to have bounded sequence, then limit inf, limit sup. Look, so this has got a subsequential limit, right? So there exists a subsequence xnk such that it goes to limit inf xn. Similarly for limit sup xn. So particularly what I'm getting, if you have a bounded sequence, because bounded sequence is limit in limit sup will be all real numbers, right? So x and k will go to this because I have got these are cluster points. You forgot. Every cluster point will be a subsequential limit. So this is Bolzano-Weierstrass theorem. Okay, this basically corollary that I proved. Every bounded sequence in R has a convergent subsequence. Okay, now look, what will you do to prove this? But I have already said that every Cauchy sequence is bounded. Every Cauchy sequence is bounded. So you take a Cauchy sequence in real line, but that I proved it is bounded, every Cauchy sequence. So that this bounded sequence will have a convergent subsequence by this result, Bolzano-Weierstrass. But right now I talked about the result. I said how to prove it. That if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself converges. Got it? So that every Cauchy sequence in R converges. So this is complete. That is the proof. Okay? You are applying the previous result. That in a metric space, if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself converges. And okay, bounded sequence. If a Cauchy sequence in a metric space has a convergent subsequence, then the sequence itself converges. And here I am with this you apply Bolzano-Weierstrass theorem that every bounded sequence in R has a convergent subsequence. This is very important. With this you get that this is complete. This is a very important result. In fact, when you prove that every absolutely convergent series, every absolutely convergent series in R is convergent. How to prove that? Okay. In fact, what you do it, look, let me tell you that one way. That first of this thing, how to prove that? Suppose you have a series this, and this is your this series, absolute terms. Okay, so that now look what I do it. Suppose Tn equal to this partial sums xi I 1 to n and Sn equal to this. Now look, Tn minus Tn. You can assume something that n greater than n. It doesn't matter. So Tn minus Tn, okay, you will get what? This I m plus 1 to n. This will come this. Okay, right? This is actually Sn minus Sn. Okay, but this series, this is this absolutely convergence. That means what? If, look, that means this series converges to a number. That if you call it S, this series converges to S. Here I am writing this is same thing as this. So that means particularly every convergent sequence is Series convergence sequence is a Cauchy sequence. It goes to 0
less than epsilon.
as nm tends to infinity, right? So this goes to 0 as nm, that means this goes to 0 as nm tends to infinity. This sequence converges, sequence of partial sums here, so that this goes to 0 as an infinity. That means you are getting this is a Cauchy sequence in R, but R is complete, so this converges. That's the proof. That's how we do it. Use it. Here now we use it. So Tn is a Cauchy sequence. So this is first, probably one of the first important applications. Every facility convergent series in R is convergent. But here I am giving an exercise that you think about it. Suppose you do not know that whether R is complete, but I give you that suppose you have it. Hypothesis that every absolutely, this is your hypothesis. You are not proving it. You are assuming every absolutely convergent series in R is this converges. Then you can show that is complete. So actually completeness is equivalent to this. Okay. It's not difficult. You can think of that, how to prove that this is complete. Okay, you can prove it. So this is equivalent to that. Okay. Actually, I have said that what is their bound. Now already I talked about bounded sets. After that, I defined bounded sets that I discussed yesterday. Okay, right? So that I'm going to the note 10. So that look, bounded sets I have already discussed. Okay, right. Now look, bounded sets, it means what actually? Now coming to this. Bounded sets in a geometric space. I said this. Suppose A is a subset of X. Empty set you can take vacuously bounded, nothing to prove. Okay, empty set. So you can assume this is non-empty. Now look, it means what you got? There exists M greater than 0 such that Txy less than equal to M for all xy pair belongs to A. Because I said you had defined diameter of A. Remember that. That is sup of Txy xy belongs to A. And if the A is called bounded if and only if the diameter, this thing is finite, a real number. That means this. That means there exists this. But this means, now look, I told you we could take a reference point. That means what? If you again you are starting with a metric space xt, A subset of X. Okay, right? Xt is a metric space, a subset of X. Now look, I can prove that I already discussed that. Suppose the following are equivalent. I am writing this way that A is bounded in X, C, B, given any point, that is for any point, given x naught belongs to X, any point, there exists M x naught, because mx, this will depend on x naught, greater than 0, such that A contained in this ball. That actually I proved, actually. You can see that. Okay. That means A is bounded if and only if it can be put inside a ball. ball. It doesn't matter whether you take open ball or closed ball. I am taking open ball. Okay. obviously it will be contained in this closed ball. Okay, so that a set is bounded if and only if it can be contained in a ball. You look at R square. To take bounded, usually you take from 0. That means there actually you take the point 0. That means if it can be put inside the ball with radius r, maybe you may need to choose big, but still you'll be able to do that. Okay, so now the thing is that, so look, bounded, that means this ball, but you are getting one ball. Suppose I have the situation that in that instead of one ball, suppose I have finitely many balls like this, but this different like this, different radius. Suppose I have finitely many balls. Okay, right? Well, you tell me that if you have this situation I give you, will be A be bounded? Here I have, suppose I am having finitely many points and so finitely many radiuses, so that many radii, so that I have this. Does it imply that A is bounded?
Yes, sir.
Yes, sir, it is
Yes, sir.
bounded.
सर रेडियस ले लेंगे मैक्सिमम ऑफ m1
Sir.
m2 m.
Radius क्या लोगे? Maximum लोगे?
Yes, sir.
Yes, sir. We can
But
take
then what will be the
maximum of
point you will
M1,
be
M2.
taking? Point?
Maximum of m1 m2 dot mn.
वो तुम है points. ये पे एक point है ना? Center. X. What will be the point here? What will be the radius here? Radius, even if you take the maximum. Okay. I am suggesting you that if you want to have the good calculation, first try for 2 balls. How to do the manipulate? Okay. How to manipulate on that? That you'll have to see that. Actually, you'll have to look at this distance also. When you are calculating the maximum of m, you'll have to take that. समझ गया क्या बोल रहा हूँ?
Yes, sir.
So that way you'll have to choose a point. In fact, you can choose any point x naught because I said that, and then you look at the distance also this. Look at an R square, how to do that. If you can do it in your laptop, you will be able to do it. Okay, thing is, so it will be bounded, fine. But the point is that now I am going to put a bit stronger condition. Here you get, this will get, that finitely many ball. Now suppose I give this condition. This is the thing. Look at definition 13, page 82. Definition 13. Look here, I am saying finitely many balls will contain A, but I am saying for any radius. That means you give me A subset of X. Of course, Xd is a metric space. For empty set, it is vacuously satisfied. Suppose A is a subset of X, and for any R, that means given R greater than 0, there exist points, finitely many points. These points will depend on R in X such that, okay, such that this finite set depend on R as well as A, okay, such that you have this. Okay, got it? Look here, the previous things here saying for any R, not only one R of that. You pick up. I will always get a finitely many balls which is containing. Okay, this is the definition. And I said here I put this. Actually, you can substitute by A, you can choose that. Okay, how to do that? That you can think of that. Okay, in R square, you think about in R square on your laptop that how to do that. This doesn't matter. So you don't need to be concerned in the definition whether I should take X or A. You can take them to be A. Okay. In fact, you can see that why you can take A. Probably you will have to take another ball with a bigger radius. Okay, to that, so that you can do that. So this, if you have this, then it is called totally bounded. It is a much stronger condition. Okay, totally bounded. And because of that, it implies totally bounded implies bounded. Because I gave you the idea already. If it is bounded, it will be same as if it's contained in a finitely many balls. So you can check that. It's usually bounded. But the thing is that this is a very stronger condition. This need not be true always. Like again, you take that I told you he is a good friend. That's for the discrete metric. ठीक है ना? Suppose you take, look, what will be the totally bounded sets here? Now look, if I take r equal to half, suppose, then you have, it doesn't matter which finitely many points if you take here. It will give you only this finite set. Look, finite set is always totally bounded, because you just pick up a point, you take any ball around that, add them, join them, you'll get that. So finite set is always totally bounded. But in a discrete metric space, what you are getting? If a set has to be this contained in this, doesn't matter what is your R. I have taken, look, I can take that. I said for all R, given R. Okay, so particularly if I take R less than equal to 1, so it has to be contained. That means there has to be a subset of this. That is a finite set. That means in a discrete metric space, every totally bounded subset will have to be finite. Okay. On the other hand, if you take the whole X, this is bounded because you have taken discrete metric. It is bounded. X is bounded. And if you take X is infinite set, then this is bounded but not totally bounded. Not totally bounded. Okay. So that this is a stronger concept of boundedness. In fact, metric space, there are various types of boundedness concepts are there. Particularly here, one, the stronger version. So boundedness may not be enough. Now the thing is that our usual metric, this distance, the familiar metric space, what happens here? What happens here? Here, later on the proof will be easier, but now you think that here a subset, if you take a subset R, A is bounded if and only if it is totally bounded. Here. You may wonder right now that why it happens. Actually, R has many nice properties which in the metric spaces do not have. That's why it happens that. So that R got this property, nice property, that A is totally bounded. It happens in that. But right now we may think of that. But the thing is that, okay, I'm not going to give you the proof of that. This proof is written here. Okay, but you should look at the proof in that. I have given an exercise now about R. Now the thing is that in metric space, everything you should have a sequential characterization. So A is totally bounded. Well, I know that. The question is that you have XT metric space and A is a subset of X. If A is empty set, nothing to do. It is totally bounded vacuously. So suppose we have this. How will I know? Check. To give definition, to give some result, that's fine. But when you go for application, to check, even if I gave this, how do I check that this is totally bounded or not? Look, here in this theorem on page 83, it is not in Aliprantis-Barkinson. Then A is totally bounded if and only if every sequence in A has a Cauchy subsequence. He said that A is totally bounded. to this. Suppose X3 a non-empty subset, okay, and looks. Characterization is very simple. Apparently, first your proof will look a bit difficult, but you should read the proof. But I will tell you about something about the trick. This is a standard technique in math. Okay, so A is totally bounded if and only if. Look, what is the statement? You take any sequence in A. It will have any sequence in A has a Cauchy subsequence. Now look, I already said in R, every bounded set is totally bounded. So look, if you use this result, then it is immediate. The why every bounded set will be totally bounded. Again, Bolzano-Weierstrass. Because if you have a bounded set, then any sequence will be bounded there. Okay, right? So bounded sequence will have a convergent subsequence by Bolzano-Weierstrass, but every convergent sequence is a Cauchy subsequence. So this will be satisfied. Okay, this is one way you can prove that in R every bounded set is totally bounded. In fact, here I should mention that if you have the metric space here, A is bounded. This is another thing you can easily check. A is bounded if and only if every sequence in A is bounded. This is just follows from the definition of boundedness. You don't need any result. That is a sequential characterization of bounded sets. A is bounded if and only every sequence in A is bounded. Okay, right? Bounded sequence, you know that. Basically, you'll have to take supremum of all these. That will be finite. Okay, right? So here the result is that A is totally bounded if and only if every sequence has a Cauchy subsequence. But now look, I will suggest you don't need to understand everything, but how the proof was being done. Okay, look at page 85. Page 85. Look here, I have given a diagram. Okay, and apparently I was going this thing. I drew a line like this. Okay, so this is the diagonal. You are having all the sequences in that, and basically I was going to the diagonal elements. Okay, this is the technique is called the diagonal method. Okay. This is a standard technique. Let me tell you that in math, 99% time basically you will be using standard technique. But of course, you'll have to learn the standard techniques. Only 1% time it will be the non-standard technique. Non-standard technique. In fact, when you go for research on that, to prove your result something, then often you need to develop a non-standard technique. But by using standard techniques, if you are good enough on that, you have learned your technique, you can prove many results. But often, sometimes it happens that standard techniques won't help. Then you need to develop your own technique. That is called the non-standard technique. So diagonal method, look at diagonal, page 85. You should look at that. After you read the proof, you don't need to understand each and every word of the proof. But if you vaguely understand what is the technique, it will be enough, good enough. Now look, diagonal method, how we use it. We have used it before actually. I didn't specify you, but I think your TA has done or not. Let me tell you that. What is there? That diagonal method, where you used it. Diagonal method.
काउंटेबिलिटी में पढ़ाई थी।
हाँ, दैट्स गुड। अरे तुम कहाँ बीएससी किया? हाँ,
डीएवीवी इंदौर।
डीयू में कौन सा कॉलेज में?
सर डीएवीवी इंदौर,
हाँ,
देवी अहिल्या विश्वविद्यालय।
विच कॉलेज?
देवी अहिल्या विश्वविद्यालय इंदौर से किया है सर।
अच्छा, इंदौर से?
यस सर।
अच्छा, you have learned a lot of things. That's good. Yes,
थैंक यू सर।
look here, this thing. Yes, you are right. This 0, 1, when you prove it uncountable, suppose not countable, suppose you assume, that means, of course it is infinite, so countable. Then you say, okay, fine, so you got an enumeration. Okay. Then you write in the, since they are between 0 and 1, so it will have the decimal representation. So you take this. I'm writing this way actually. X1 like this. This is because of X1. X1, 2. You could take X1, 1 also. Okay, that will be the better, I think. That will give you the diagonal sense. So that X1, 1, X1, 2 like that. Okay. Similarly, X2, 0 point, X2, 1, X2, 2 like this. Okay. In YAL you go for X. Now look what I'll do that. Now I'll make a change. I will look at the first element here. If you can choose that either it is a 0 or not. If it is 0, you replace it by 1. Okay, if it is 0. Okay. If it is 0, if x1 was 0, then replace it. You could do it many ways. Then replace it by 1. And if it is not 0, then then replace it by 0. Okay, right. Here you should have another thing to be careful. Like when you have 0.499, I am not going this. That is equivalent to same as 0.5. So keep that in mind. But that's why I am putting 0 and 1. So if you have 0, replace it by 1. And if it is not 0, then replace it by 0. Okay, so you are changing. Next thing also you are changing here. Okay, now you take this thing element, a new number, 0 point, look, whatever I am getting, this thing, replace, you are not replacing, I am saying you pick up that number. Okay, so we are getting a number here like Z1 here, Z2 next time, Z2 here. Okay, now look, this is again lying in between 0 and 1 because I have taken the decimal on that. Okay, but then if it is countable, it should be one of them. But it can be none of them, at least at one place diagonally. It is different. That's the way I play the trick. Okay, so it is different. Okay, so that it can't be countable. But look here again, I have applied this diagonal thing. Okay, got it. So diagonal method, even in very advanced level mathematics, is a very useful technique, standard technique, but it's a very useful technique. So I gave this proof to emphasize. In fact, most of the time I do not think you need the proof. You just need the result, big result, that it is totally bounded if and only if every sequence has a Cauchy subsequence. But I want to emphasize the technique in that is diagonal method. That's why I have written so much about this. Okay, so this is diagonal method. Fine. Okay, so that you got this. Now recall that I have already counted. I already gave you that separable dense subset. And separable metric space. Okay. If you have this and A is a subset of X, then A bar equal to X if then A is called dense in
X.
Now suppose, not for all, suppose there exists a countable infinite, countable n, such that a bar equal to x. Then x is called, more precisely, xt is called separable.
Separable.
Fine. So that in R, you know, Q is dense in this. Not every countable set will have to be dense of that. I am saying one, I just one, there exists, means one. Here you have seen that Q bar is R and Q is countable. So that this is separable.
R.
Okay. In fact, this is also a good result. By using this, you can prove that Rn with the usual distance and Cn, they are all separable. Okay. Here basically you use the fact, if you have n sets that each like this, and each of them is countable, then this is also countable. That's why the
Countable.
basic things I have taught you before.
Countable.
Those things you need. Okay, these things you need to prove that this thing and fact that R is separable, to prove that Rn or Cn they are separable. Okay. Okay. Now, what is the link with the totally boundedness? I have given exercise. Discrete metric space is separable if and only if X is countable, because in a discrete metric space every subset is closed. So if you take a discrete metric, you see that if you take a subset of X, then A equal to a bar, because every subset is closed, right? Okay, right. So that what will happen? So if you want it to be separable, then this A has to be countable, right? That means the discrete metric space cannot be separable unless it is countable. So if you take uncountable, like R is uncountable, on this if you give discrete metric, this will be not separable. Understand? Look, R with usual metric is separable, but with discrete metric is not separable. So that if you change the metric, you get a different metric space in that. Okay, right? Fine. Now the thing that look at the theorem, every totally bounded metric space is separable. Okay, later on you will use a technique for compactness, same technique. So that how I proved that. Look, proof is very simple, but the technique look, so that here the result. I'm saying this is good, but a separable metric space need not be totally bounded. The whole thing is not totally bounded, but it is separable. So its converse need not be true. Every totally bounded metric space is separable. Look, R is not totally bounded because it is simply not bounded. Every totally bounded metric space will have to be bounded, but this is not bounded, so it is not totally bounded, but it is separable. So that converse of this result is not true. Okay, that you should understand. A separable metric space need not be totally bounded. Okay, now the look how I am going to prove it.
Totally blocked.
Say again. I am saying I want to prove it. Now look how I am going to prove it. So that you choose 1 by n, you just use the definition. Okay. Here whole set is X. X I am saying every totally bounded metric space XD. So look here, when for a subset I am having this. Okay. But if A equal to X, everything you are working inside X. So if you replace A by X, then X has to be equal to this. Okay, the union. So you take R equal to 1 by N. So you get a finite set that I am calling Fn, because this is how to write nicely. I won't take x1, x2 because n, that may not be n, some xm, but I need finite set so that you will get this thing. Where x belongs to a finite set. This finite set depends on n. The finite set. Fn is finite. Okay, x is finite. Now you are taking f equal to this. Okay, over all n. Now look here, I am using the result previously I taught you. Each of them is finite, and this is countable union. Countable union of finite set is again countable. So f is countable. I taught you whatever is needed. I didn't teach you anything extra. You should understand that. Huh? I was not teaching you any bakwas. समझ गया?
Yes.
Then you will think, if I didn't teach you, then you will wonder how it is coming in that. Okay, so this is countable. Now my claim is that f bar is equal to x. So then I'll be done. Look how I did that. It is simple triangle inequality. Make sure that you understand that. Okay, look here, the trick is if you have dxy is less than r, look, x belongs to byr implies txyr, but that also means implies y belongs to bxr. समझ गया? I can interchange. Look here. That is clear from the diagram. You have this x, y, so you have this is your r, that means x is somewhere here. Then if you take this big r, this will come, but this distance is less than r. So if you take a radius with this r, then this will contain this one. So this is the thing I have used basically. Look, note that in the end x belongs to byn implies duxy less than 1 by n implies y equal to y belongs to bxyn and this. And look, given r, you'll have to prove that given any r dense. Now look, f bar equal to x means what? That means any point of x is a closer point of f, right? Because f bar equal to x. That means if you check this, this has to show that x is a closer point of f. But that means what? X is a closer point of f means by definition you'll have to show that for any r given r greater than 0, that means any r given in r greater than 0, intersection f not equal to 5. That you'll have to show. Now this r, any r, so I have chosen 1 by n such that this. Okay. Now look, remember that the way I have got it, x equal to union b y 1 by n, y is the finite set given this. This I got. Okay. Got it? Okay. X equal to this. Now look, we took any x, so x is here. That means x will belong to this union. That means there will exist, right? This thing. There will exist y. 1 by n is fixed because 1 by n I have got from here. And here I have used total boundedness definition. Look, I can do that simply. This I have used, this I got because x is totally bounded. You should be careful why you are getting something, what you are using. In the beginning, you should check your steps that, okay, this I have so that I am getting it. So here you look, totally bounded. Now, but x belongs to x, then x belongs to this, then x belongs to one of the balls. Okay, so there exists y, that exactly that. If not even done, then this y will belong to that. Look, now look, that I already told you. Right? But this is contained in because 1 by n less than r. But y is in Fn. But Fn is a subset of f. So y belongs to f and y belongs to be xr. So that is not empty. समझ गया? The proof is very simple. So make sure, I am telling you again, this proof you should read again, this theorem. समझ गया क्या बोल रहा हूँ? This theorem proof, make sure you read again. देखो, let me tell you something philosophically that word. Mathematics only you have so-called big result, call it usually the big proof. But big proof, let me tell you that it's just a combination of many small proofs. It's just a combination of many small proofs. So that when if you go on to understand the big proof of a big result, you should be able to understand the first small proofs. That's why like this kind of result theorem, you should be able to understand the proofs. Then you will understand this. Understand? That's why I always tell you that when you do mathematics, first you see the definitions, read the definitions carefully, then you read some examples. First try to understand the examples, then you go for the results, small results. So the proofs are probably 2-3 lines. You see that whether you understand the proof. And then gradually you go for bigger proofs, bigger results. Okay, so this theorem, later on I will use this technique. Okay, I am telling you the technique I have used. I can use later for the same technique for compact metric space. I have not taught a compactness. So when I teach you, so this is the same technique, only not only same technique. In fact, writing will be same, only 1 or 2 places you will be changing some word. Otherwise, it will be ditto same. That technique also, if I teach you so-called Lindelof metric space, that is like separable metric space, that is also there. Okay, right? So you think of that. Okay, so make sure this theorem technique if we prove it on that. Okay, and exercise I say, can you find a separable metric space which is not totally bounded R? Okay, right? That I already discussed on that. Now, just we will explain the proof now. Look, what I have given total boundedness, totally bounded. I have given you a sequential characterizations that every sequence, if it is totally bounded, every sequence in A has a quasi subsequence. This is called a sequential characterization. Sequential characterization of total boundedness. Okay. In fact, in metric space, you always try whatever concept you define, you see that where we can get a sequential characterization, because sequences is easy to handle. Look, again, I am telling you, I can give you many definitions, I can give you many results, but when you try to apply, then you'll have to see whether I can easily apply. Okay, how to apply that becomes important. If I have give you a big result and big thing, big definitions, then you don't know how to apply it, then it is not useful. You should know how to apply. Okay, right? Here, let's forget I am telling you that in mathematics another philosophy is there. Suppose when I am talking about applications on that, you have a result, suppose, and look what will happen. Hypothesis, I have hypothesis and then I have something conclusion, proof that this is. Now look, you say how many hypotheses I should have it. Here it should. But I say I will use a word vaguely that optimal. Look, if I have many hypotheses, suppose I have many, then obviously you can have a good conclusion. You can have a good conclusion. Okay. But then when you go to apply, somewhere in the situation you say, okay, suppose you have having 4 hypotheses you are taking. Suppose to be specific. Then you see that whatever I am doing, I am never getting 4 hypotheses satisfied. I am getting at best 3, 2, not 4. Then what is the use? That means you won't be able to apply this theorem. Then you say this theorem is bakwas, it is not a good theorem. That means what will happen? Basically, our result should be that under minimum number of hypotheses to prove something. Okay, so that you can apply to more places. Okay, that is like if I have under 2 hypotheses, suppose conclusion may be weaker, not as strong as you are expecting, but still it will be a good result because only you need to have satisfied 2 hypotheses and you can still have some conclusion. Whereas in 4 hypotheses, I can have a strong conclusion, but you see that it is never satisfied or very rarely satisfied. Then what will be the use? So that this conclusion will depend on how many hypotheses you are taking, and that is also will depend on that practicality of the result and that how many times you can apply the result. Okay, so that don't think the result is something. When people mathematicians say it's a good result, you should know what is the meaning of the good result. If it is applicable to many cases, then only it becomes a good result. That is the necessary condition for a good result. Now look, now coming back to the sequential characterization, I said closure point. I have given you the definition. You said that is not a very difficult definition, that A is a subset of X, XD is a metric space, and X belongs to X, then X belongs to A bar, if and only if this we have this. Non-empty for all R, that is for any neighborhood of X. Fine. Still I will prefer, okay, this is not very difficult, the definition, you can check. But still I will prefer something very simpler, particularly sequence. That means sequential characterizations of this. Okay, sequential characterization of closure point. That is, now look, if suppose you start with the easier side, fine. Then you are considering this. Also look at the technique 1 by n intersection A, okay, not equal to phi. Fine, got it? So that it is non-empty. So I can pick up an element here. So that suppose there exists that I call, because if it will depend on n. So there exists xn belongs to Vx 1 by n intersection A. Now look, it means what? Xn belongs here, that means dxn x less than 1 by n, and xn also belongs to A. Look at the trick. For each and now we are doing this. That means we are getting a sequence in A. Got it? And look, this trick will tell me what? This is true for all n. That means xn goes to x. Right? You look at this technique. This is a standard technique in metric space. Okay. So xn goes to x. That means what I am getting? If x belongs to a bar, I am getting a sequence in A such that xn converges to A. That means I am getting this. Implies there exists a sequence xn in A such that xn goes to x. Okay. Look, that means if the closure point, if I have, you have this. But what about the converse direction? Suppose I have it, will be to a closer point. That is also true, and that is actually easier, because look, if I have this, xn goes to x, xn is a point. Suppose I have it. I want to prove this now. That xn goes to x means if you take any ball, pxr, around x, neighborhood of x, it converges to x. So by definition, it contains the tail of the sequence, right? That means there exists xn. Actually, what? That xn belongs to bxr for all n greater than equal to nr. ठीक है ना? I am using the definition of the convergence of the sequence. Okay, since you are assuming xn goes to x, so the given r, there exists nr. Given r, there exists nr such that you have, in particular, you are getting what the xn is coming from a, and that means in particularly you are getting a intersection bxr is non-empty, implies x belongs to a bar. Got it? That means what you got?
Yes, sir.
You combine them. That means x belongs to a bar if and only there exists a sequence xn is such that xn converges to a. That's it. The trickier part is here. This part is easier. It follows from the definition. This part. That means I have got this result. That is theorem 6.9 here. I am saying page 87, part A. What I have got? I have got this. X belongs to a bar if and only if there exists a sequence xn in A such that, look, proof is easy, so that you should read the proof again, such that xn goes to x. That means x will only be a closure point if and only if there exists a sequence xn in A converging to A. Okay, like here, look, in R, if x is already belongs to A, then you can take sequence xxx as constant sequence. So if you take this, like if it is in between there, it's not a problem. But if you take 0 is a closure point. So you have this particular sequence 1 by n going to 0. 1 by n is coming from A, right? Similarly, 2 minus 1 by n, this sequence. This is coming from A and it is converging to 2. Okay, so this is a sequential characterization of the closure point. Closure point. Okay, sequential characterization of the closure point of view. Now look, I told you special kind of that I will do next time, but let me tell you that what will be the problem now. Okay, now suppose this is an accumulation point. Okay, right? Of course, if this is a closure point, you will get this. Okay, but if you come this way, you may not have a closure point. Okay, like I told you that if you take this thing, I will have a sequence converging to constant sequence, but that may not be an accumulation point. But then you say, oh, actually here it is getting constant sequence. You are not getting the distinct members. That means look at the accumulation point. Look at the statement B of this theorem. X is an accumulation point. Look, I have picked up elements from here. But you think about it. I have never bothered whether, even if I suppose I am taking this. Okay, there I am choosing xm. nm different. But I didn't bother to check whether I am picking up the same thing or not. It's quite possible, right? That you pick up the same thing. xn. Okay. I have a ball. Then you have another ball here, bigger, smaller radius. This is your x. This is 1 by n, 1 by n. You may not know that you may choose this point for both the balls. Okay. So that means the way I picked up, I didn't guarantee that I am picking up distinct elements. I'm picking up distinct elements. So suppose I can guarantee that each time I can pick up distinct elements. Then what happens? Okay, here I may not have that choice, like here. I won't have that choice. I can't pick up distinct elements. But suppose I can pick up distinct elements of the sequence, then it will be an accumulation point. Look, X prime belongs to the derived set of A if and only there exists a sequence of distinct terms xn in A such that xn goes to xt. Okay, I will prove that. By the time you can read the proof yourself, but let me tell you that how do you choose the distinct points in that? Look, remember that the accumulation point. Accumulation point, if you have this, it means what? If you take any r greater than 0, that means you are getting what? That A minus X intersection B XR is non-empty. Fine. Okay, got it. Or else you can write that. You can delete here. It is called deleted neighborhood, and then you can take it. Okay. Now look, it means if I have this, now suppose for radius 1, r equal to 1. That is 1 by 1. Okay, this is x. So you are choosing something here, getting a point other than x. That's by definition. So get a point x1 belongs to this intersection, this thing. Okay, suppose this is your x1. Okay, x1 is other than x. That means particularly dx x1 greater than 0. So since x1,
Yes, sir.
okay. Now look, if I want to pick up x2 distinctly from x1, then what will be my trick? I will choose not, if I choose r2 equal to half, here I could have x1 here. So this is not enough. Then what I will do that? Suppose now I'm choosing, but at the same time I need to choose a sequence like the previous technique. The distance between x and xn has to be less than 1 by n. Only then it will guarantee that xn converges to x, right? So that, but if I take r2, that I'll have to take anyway r2. But I am not very sure that whether I will, here I have written that. I do not know that. Suppose we are having this half. But you even never knew that it probably could have this here, x1. They probably you chose x1 here. Then what I will do? Okay. Now look, this is positive. This is positive. Not what I need to do. I need to exclude x1. Then I will choose a ball like this, so that x1 is outside. That means my R2 should be not half. It should be minimum of half and dxx1. समझ गया?
Yes, sir. Yes, sir.
If you now you choose this bxr2, by this you will get a point x2 in this. I am explaining the you to the technique and that. Okay. R2. Look. Then what will happen? Because of this, you have taken the minimum of that. X2 will be, look, first of all, from this definition, X2 not equal to X. Then you have chosen, look, it means X2, dx1, dxx2 less than R2. That means particularly less than this. That means X2 not equal to X1. समझ गया? This means distance between x and x2 less than r2, but r2 is minimum of this. That means this is less than r2. Okay, less than r2. That means less than equal to this. That means we are getting this thing dx2 x strictly less than this. That means x1 cannot be equal to x2, because if x1 equal to x2, then they will be equal. So that means you are getting x2 not equal to x1. Same technique you will be doing, but ultimately you need to do by induction. For x3, what will happen? Look, I have already come. That x3 I'll have to take minimum, look, 1/3 dx x2, minimum of 1/3 dx x2. Another stage that will come. Okay. Look, another thing. Why I need to take minimum of this? This will guarantee that xn converges to x. Here, my job is little more difficult. I not only I need to choose a sequence converging to x, I need to choose a sequence of distinct points. Distinct points. That's why I am playing this trick. This is a standard technique in metric space. If you want to pick up a sequence of distinct elements, you don't need to understand line by line or mug up. Just see that how I did it. Exactly. What I did here in the note, I explained to you the technique. Here you need to ensure two things: the sequence converges and sequence has distinct elements. Other way it will be immediate. Okay. This way, when you construct, if you have this, you will have to construct a sequence of distinct elements converging to x. But other way, like if you have this, that will be immediate from the definition. So make sure you read that technique. I will again explain on that. I will talk about the regions. So that you are getting sequential characterization of accumulation points also. Okay. That's the thing. Sequential closure point, sequential of accumulation point. That you should. So that in the exam, I will give you simple questions, but you will have to learn the techniques. So you need to know. You can look at your notes. So what are the techniques? If you can figure out, oh, this is the technique I have to use, then it will be very simple. Just you go to my note and okay, this is the technique. Okay, got it? So that basically I want to teach you techniques, not only just theorem. समझ गया? So that make sure that you read that. Okay. So I will take the next class on Monday. ठीक है? Okay. I don't know. I sent you the invitation. I think for today. I couldn't find it here. I don't know. Did I forget it? No. Okay.
No, sir.
Then I don't know
No,
why
sir, we got it.
laptop I couldn't see it. Okay. I will see you Monday. I will send you the invitation. ठीक है? Okay. So I will continue
sir.
from this and page 89, the completeness. Okay. See you. Bye.
Okay, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.
Have a good day.
You are welcome.
Thank you, sir. Have a good day, sir.
Gondor plus 3. Yes.